detours. Let's get to today's actual material. Last lecture for the book.
Yay.
So today we'll be covering exponential functions, and then we'll be covering very simple differential equations, what are called separable differential equations. So starting out with just a quick reminder from last time. Introducing you to logarithms. I know that typically you don't get very good exposure to logarithms in earlier maths like you should. So reminder, what is log base a of x equal to y mean? X is your product, a is your base, y is your exponent. Remember, logarithms take products and spit out exponents. Exponentials take exponents and spit out products.
Yeah.
So when we say log base a of x is equal to y, that's logically equivalent to x is equal to a to the power of y. Okay. In the special case where our base is e, log base e of x is what we meant by natural log of x. It's just a log where the base is e. Good?
Oh, well, what's the definition of E again, sir?
E, we won't need to remember its definition going forward from here on out. The e was the limit as n approached infinity of 1 plus 1 over n to the n.
Oh, right, so compound interest.
That's one way to see it. Anyways, and so logarithms and exponentials undo each other. They're inverses of each other.
Yeah.
So the natural log of e to the x is just x. Natural log of e to the x is saying, what exponent do I need to raise e to get e to the x? Right?
Yeah.
And similarly, e to the natural log of x is just x. Those are inverse functions, they just undo each other. Okay. And then remind you of our change of base formula. If I have log base a of x, we proved this last time, and I want to change the base from a to b, that's the same thing as log base b of x over log base b of a. In particular, we like working with natural logarithms, so here's a common substitution. Rather than having log base a of x, you're going to write that as log base e of x over log base e of a. Replace your b's with e's. Gives you this equation. Common substitution. Because we like working with natural logs a lot more than we like working with logs of some other base.
Okay.
Remind you of some proofs we did last time. One of the proofs we did is that the derivative of the logarithm log base a of x is equal to 1 over x times log base e of that special number e. When we did this proof, this exact limit showed up, and when we calculate that limit, we replace it with e. Now, using this exact change of base formula, log base a of e, replace our x's with e's. What's log base a of e? It's the natural log of e over the natural log of a. It's the natural log of e, which is 1, over the natural log of a. So when you look up this derivative in your book, your answer is going to be that. What's the derivative of log base a of x? It's 1 over x times 1 over the natural log of a. You can also calculate it this way if you want it. Perfectly fine. That's what we proved the result was last time. In the special case where we're talking about the derivative of the natural log of x. What's the derivative of the natural log of x?
Just 1 over x.
Yeah, just following this formula, it's 1 over x times the natural log of e. What's the natural log of e? 1. Or if we would have thought about in terms of this formula, what's the derivative of natural log of x? Well, it's 1 over x times the natural log of our base. Our base is just e. Natural log of e is 1, 1 over 1 is 1, and so once again you get 1 over x. Okay, just to give you some picture to keep in mind with these functions. If f of x is the function e to the x, then g of x equal to the natural log of x is going to be its inverse function. So here's f of x, here's g of x. Notice f only spits out positive numbers. If I take e and I raise it to some power, it's always a positive number. If I raise it to a power like -10, that's the same thing as 1 over e to the 10, which is 1 over a big number, which is a really small number. So when you try plugging negative 10 in here, you're going to get a really small number. You're never going to get a negative number. Similarly, with our natural log here, we cannot take logarithms of negative numbers. When I say what is the natural log of negative 2, I'm saying e to what exponent equals negative 2? What's the exponent I can put here that gives me negative 2? The answer is there isn't one. I can't take e to some power and get a negative number out. Whatever power I raise e to, it's always a positive number. So logarithms can't take this. Now on your calculator, I don't know if you've ever come across this before, typically you have an exp button. And you place an x in it. That is how you do e to the x on your calculator. Make sense? Okay. So let's quickly go through some example problems just using these, and then really quick do the theory, and then just a bunch of example problems after that. All right, so starting with this problem. So we have e to the 2x minus 6 is equal to 4. How on earth do we solve this thing?
Find x.
Right, how do I get x? I can't divide both sides by e. That doesn't really do anything.
You use your logarithms.
So what exactly do I do? Notice that my x is in an exponent up here.
Yeah.
I'm trying to get the x by itself on one side. That's the way you solve these types of problems. How do I get the x by itself?
Log.
What do you mean log? You're just throwing out log, hoping that's the answer.
It's the
It's part of
natural
the answer.
logarithm of 2x minus 6.
Yeah, let's take the natural log of both sides. What is the natural log of e to the 2x minus 6?
2 minus
Equal to, and we got natural log of 4 over here.
So
What is the natural log of e to some exponent?
the exponent?
It's just the exponent. The natural log of e to anything is just that thing.
Yeah.
So this is just 2x
6.
minus 6, which is equal to the natural log of 4 is the same thing as 2 squared.
Yeah.
What can I do with that squared?
Move it front.
Bring it out front. So I get 2x is equal to 2 times the natural log of 2 plus 6. I'm going to plus my 6 over here.
Yep.
Yeah.
Divide everything by 2, and finally I get x is equal to the natural log of 2 plus 3. There it is.
2 plus. Oh.
Yeah, because we moved the 6 over there.
Wait.
Wouldn't
Oh,
it-
that's the natural log of 2 plus 3.
Oh, yes. So
Yeah.
when I don't do parentheses, it means just the thing that immediately follows.
So that's not the natural log of 2 plus 3.
No.
Oh, right. Okay. Obviously.
I'll be very lazy about those. If it applies over a sum, I'll put the parentheses.
Okay.
And if it applies over a product, I always put what we're multiplying out front. Similar to how we do sines and cosines. We get real lazy with our parentheses. Okay, so our next problem here is, that was awful. I'm trying to get a little bit more straight. That wasn't much better. We've got, here's the natural log of x. It's a lie, but there's the natural log of x. Our job is to find the line that is tangent to it and goes through the origin. So I'm looking for the line y equals whatever that is tangent to this line and goes through the origin. You with me? So what is the equation of this line? That's what we're looking for. Okay, so it must go through some point here, let's say over here at A.
Okay.
So if our function, f of x is equal to natural log of x, what's our derivative?
1 over x.
Just 1 over x. The derivative of natural log of x is 1 over x. So what is the slope of our line at A?
1 over a.
So our slope has to equal 1 over A at the point A. Right? Now let's calculate our slope another way. If I go over A, how high up am I?
Y.
If my function is natural log of x. If I go over A, how high up do I go?
Y, which is your natural log of x.
Well, y here is to figure out for the line. But so how high up am I?
You're at the y, whatever that.
What is it? Here's my function, f of x.
Natural log of a.
It's just natural log of A. Come on, guys. What does a function do? It gives you the height at any point. What's the height at A if my function f of x is natural log of x?
It's A. Huh?
It's natural log of A.
Natural log of A.
Okay, let's start thinking. Our brains going?
Trying.
Okay, so I know the slope is 1 over A, but I can also use rise over run.
Yeah.
What is the rise to get from here to here? How high up did I go?
Natural log of
Natural log of A. What was my run?
It's A.
A.
It's A. So now I know whatever this A is, it has to satisfy this equation. The slope is 1 over A, and the slope is also natural log of A over A.
Natural log of A has to be 1.
So we can figure out what this A is. We're trying to figure out what that point is, where it's tangent to this function. So natural log of A has to be 1. Multiply both sides by A. So I get 1 is equal to natural log of A. More importantly, what does A have to be? What is the number whose natural log?
E.
It has to be E. A has to equal E. What is the natural log of E?
Oh, yeah.
1.
What is the exponent I have to raise E to get E?
1.
1. Okay, so I now know that A is equal to E. So what's the equation of my line? My line is y is equal to m. What was my slope? 1 over A, which we saw for was E. 1 over E times x. Its y-intercept was 0. So here's the line tangent to the natural log going through the origin.
A equals E or the natural log of E?
A had to equal E. So that the natural log of A was equal to 1.
Yeah.
So that 1 over A was equal to natural log of A over A. So that the slope was equal to the rise over the run.
Yeah.
Okay. All right, with that little bit of warm up, let's do all of our theory that we need to do for the day. We have 5 proofs that we've got to do, and only 2 of them have any meat to them. So our first proof, we are now going to find what is the derivative of a to the x. I'm going to prove it's a to the x times natural log of a. Okay? So we are looking for the derivative with respect to x of a to the x. And, well, how best do I want to say that? That's fine. But let me just say y is equal to a to the x. And now we're trying to figure out what y prime equals, right?
Yeah.
And we're trying to prove that y prime is equal to a to the x times natural log of a. That's what we're trying to prove. Okay, that was a to the x. So first thing I'm going to do is we've already done an approach like this before. Huh?
Take the natural log.
Take natural logs of both sides.
Yeah.
So then the natural log of y is equal to the natural log of a to the x, or bring the x out front.
Just x in front.
With me so far?
Yeah.
Now let's calculate our derivative. What is the derivative of natural log of y?
1 over y.
1 over y
Sorry.
times the derivative of y with respect to x,
Which is just
which is y prime. And that's equal to, what is the derivative of x times natural log of a with respect to x?
X times just x over a.
x over natural log of a over.
Natural log of a
X.
is just a constant. It's just a number.
Oh.
Oh, so
So it's
just x.
So it's just x. Wait, 1. Remember.
You're getting closer.
What?
It's not a, it's not 1.
It's
What is the derivative of x times 3 with respect to x?
3.
3.
3. So natural.
Oh, so just natural.
So it's just natural log of a, guys. It's just a constant.
Okay.
Holy crap. Okay.
Okay, back to thinking.
Yep.
I'm really trying to.
X times a constant, take the derivative. What's the derivative of x with respect to x? Let's calculate that. The derivative of x with respect to x.
32.
1. What's the derivative of the constant with respect to x?
Constant.
Just a constant. Okay,
We good.
good. All right, so now we got this. Remember, we're trying to figure out what y prime equals. So multiply both sides by y, and I get y prime is equal to y times natural log of a. Now, what was y? A to the x. So this is equal to a to the x times natural log of a. So, what is the derivative with respect to x of a to the x? It's still just a to the x, but then times natural log of a.
Oh, that's interesting.
All right. Now, let's prove the next one. What is the derivative with respect to x now of e to the x? We proved it for any base existing. Now what about for the special case where our base is exactly the number e, 2.7 blah, 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 blah. It's exactly e. Now what's the derivative of e to the x with respect to x? Well, just use our formula. It's just e to the x times the natural log of e,
Which is 1.
which is 1.
Also, it's e to the x.
It's just e to the x. This is another way that you come at a definition, or at least a notion, for what this function e to the x is. What is the function f of x equals e to the x? It is a function that grows at the same rate that its slope increases. The height of the function and the slope of the function are the same at any point. If I come look at this function, and if I was careful enough in my drawing, if I come over here to figure out its height, however high it is, its slope there is the exact same thing. So the height of this thing at 2 will be roughly 8-ish, somewhere around there. And so the slope here should be pretty much 8. The height of this thing at 0 is 1, and so the slope of this thing at 0 should be 1.
Yeah.
Furthermore, if f of x is equal to that, not only is its derivative equal to that, what about its second derivative? What's its concavity equal to?
E to the x.
E to the x. And not only that, its third derivative is e to the x, and its fourth, and its fifth, and its sixth, and take all the derivatives you want. They are all e to the x.
Yeah.
Let me give you some physics applications. Let me say that I have some particle. F with respect to time, I'm counting how many meters it moves away. And it is moving away in such a way that it is going e to the t meters away from me every second. So after 1 second, it's 2.7 meters away from me. After 2 seconds, it's 2.7 squared, roughly 8 meters away from me. And it keeps going and going and going. Question, what's its velocity then? E to the t. What's its acceleration? E to the t. What's its jerk? E to the t. All the way down. We love exponentials with base e. Nothing easier to work with.
Yeah.
One of your quick sanity checks, if you're ever talking to someone who pretended they know their calculus, just ask them, what's the derivative with respect to x of e to the x? If they ever say, I don't know, it's complicated, I have to think about it, it's pretty obvious that they haven't mastered their calculus. It's one I use all the time when someone tells me, oh yeah, I know my calculus. My first question is, what's the derivative with respect to x of e to the x?
Do you run into that problem a lot?
Yeah, I talked to you guys, and you guys all told me you took geometry once.
No.
We did not say that.
I don't know.
We took algebra. She took geometry.
Whatever it was, I get kids telling me that they took classes all the time, but they already know that material. Oh, I already know geometry. Ask them some basic questions about geometry. Let's discover.
That's funny.
So yeah, I get people telling me they know the calculus. Okay. Let's see, we did that. So we did this. Now let's go the other way. Okay. What now is the integral of e to the x with respect to x? Now this is much harder. Well, we have to find an antiderivative of that thing.
Yeah.
So we need to find some function whose derivative gives us e to the x.
E to the x.
It's e to the x
Plus C.
plus our constant.
Oh, yeah.
Y plus the constant. What's the derivative of the constant?
0.
0. So here are all possible antiderivatives of that thing.
It's 1.
It's a family of functions who, when you take their derivative, gives you that.
Yeah, right.
Okay. And just remind you that derivatives of constants are 0, just in case.
It's plus 1.
And then, let's now do the integral of this thing. This is easier to come at a different way. Let's look at the derivative with respect to x of a to the x over the natural log of a. With me so far?
Okay.
A here is just some number, like 7,
Okay.
right? Natural log of a is a
Constant.
constant, so we can just pull that outside the derivative. So this is just 1 over natural log of a times the derivative with respect to x of a to the x. Okay, what is the derivative of a to the x with respect to x?
It's a to the x times the natural log of a.
It's a to the x times natural log of a. So this is equal to 1 over the natural log of a times a to the x times natural log of a. Natural log of a's go out, and we're left with a to the x. What was the point of all that? I found some function whose derivative is a to the x. You with me?
So now you have the answer.
So this is an antiderivative of that.
Sweet.
So now, what is the integral of a to the x with respect to x? It's equal to, find some antiderivative. Here's one.
How are you supposed to know that on the top of your head?
It takes a little bit of cleverness.
How would you even know to go there?
We just need to find some function whose derivative comes out like that. We had a function whose derivative came out like this thing. And so we were almost there.
Yeah.
And so just that thing, and so you see, oh, I just need to somehow cancel out my natural log of a. And then we'd be there.
Okay.
So it's being a little bit clever, but it's not that hard to come up with the function if we would have stopped and thought about it. Maybe I should have approached it that way. But there it is. Okay, so we did that, we did that, we did that. Common useful substitution. So I told you this one. Anytime you have a log base a of x, it is very common practice to say, I don't want to work in logs in any base except e. And so to just replace it with natural log of x over natural log of a. It's very common to just do that first thing and not even try to think about logarithms and other bases. Similarly, it is very common to say, I never want to work with a to the x.
Why?
I want to work with e to some exponent, not a to some exponent.
Okay.
And it's a very common substitution. So here's how we do it. First off, look at this piece. What is e to the natural log of a?
E to the natural log of a.
Yeah, let's write that separately. What is e to the natural log of a equal to? What is e to the natural log of x equal to?
E to x.
Just x.
X.
E to the natural log of something, the e's and the natural logs cancel each other out.
Yeah.
The same way that the natural log of an exponential of an exponent gives you the exact same as an exponential of a natural log of an exponent.
So a.
Yeah.
Yeah, just depending.
So it's just a. So this is just a fancy way of writing a. So I'm going to take a here. I'm going to replace it with a fancy substitution. E to the natural log of a. So a to the x, a to the x. You with me?
Yeah.
Yeah.
Now when you have exponents to exponents, that's the same thing as multiplying the exponents. So rather than having a to the x, you're going to have e to the x times natural log of a. Very similar to, instead of having log base a of x, you're going to have natural log of x divided by natural log of a. Common substitution. You get stuck on a problem. If it's got logs, try to replace them with these. If it's got exponentials, like this, try to replace it with these. Okay. So with that, let's now prove something that we've already been using. We're going all the way back to prove our power rule. Remember our power rule?
For derivatives.
Yeah, for derivatives. So what is a derivative with respect to x of x to the n equal to?
Just n minus
N
1 on
minus
top and then n pulled out in front of that.
Like that, right?
Yep.
Now when we did this proof, we only did it for natural numbers as our exponent.
Okay.
Yeah.
Now we're going to prove it in general. For any real number n you pick there. Okay? So we are looking for now, what is a derivative with respect to x of x to the n? Now, using the substitution, x to the n is the exact same thing as e to the natural log of whatever our base was. What was our base in this case? X. And then times n. Sorry, put the n out front. N times the natural log of whatever our base was. Our exponent times the natural log of our base. You see the substitution?
Yeah.
Okay, so now the derivative of this is just the same thing as the derivative with respect to x of e to the n times natural log of x. What is the derivative of e to something?
It's
It's
to
e to something.
It's e to that thing,
Yeah.
Times.
and then chain rule times the derivative of the inside. What is the derivative of n times natural log of x
Wait, what?
with respect to? Just doing the chain rule.
Okay.
Natural log of
So now we gotta do, look, if I did the derivative with respect to x of e to the 3x, what would that be equal to? E to the 3x
Times 3.
times 3. Carry out your chain rule.
Okay. Fair.
Wouldn't that be 1 over x?
So, okay, up
1
here,
over x?
you're talking about this, right?
Yeah, 1 over x.
1 over x.
Times n, which is n over x.
Oh, you're saying n over x. Yes, n over x. Perfect. Carrying out the chain rule. Everyone see it?
Yeah.
Now, e to the n times the natural log of x is exactly x to the n. So this is still just x to the n. We have times the n here, and then divided by x. Right?
Mm-hmm.
Now what is x to the n divided by x?
X to the n minus 1.
What is going on?
All right. One step at a time. Resubstituting this back with x to the n.
Oh, okay, yeah.
Okay, that is equal to n times x to the n over x. Good with that?
Mm-hmm.
Okay. Now, what is x to the n divided by x? What is x to the 5 divided by x?
It's going to be x to the 4. So it's x.
Just x to the 4. This x cancels out with one of those x's, leaving 4.
Yeah, yeah.
So it's x
So
to
this
the
is
minus
equal
1.
to n times, we're going to cancel out one of those x's, leaving n minus 1.
Yeah, sure.
This x, how many x's do we have up here?
1.
This is x times x times x times x, n times. We have n x's up there.
Okay, unknown.
This cancels out one of them.
Yeah, but what?
So if I have n M&Ms in a bowl, and then I eat one, how many M&Ms do I have left?
N minus 1.
N minus 1, whatever that number is.
Yeah.
So we cancel out one of the x's, leaving n minus 1.
What if x is 1? Or what if n is 1? It's
Then it
just-
still works.
Okay.
Let's handle the case where n is 1,
Okay.
right? So you're saying, what is the derivative with respect to x of x to the 1 equal to?
0.
No, it's equal to 1 times x to the 0. What is x to the 0? 1.
1. That's right.
1 times 1 is 1. So there you go. Handle the case for 0.
Yeah, that makes sense.
So this works for any positive number x. Why does x have to be a positive number? Because we're taking the natural log of it. And you can't take a natural log of a negative number.
Right.
Okay. Let's see. We did that, we did that. Okay, there we go. There's all the proofs. Now we're just going to do a bunch of examples using the proofs over and over again. Okay. What is the derivative of 5 times e to the x?
5 times e to the x.
Yeah, what's its derivative?
5 times e to the x.
Yeah, 5 times e to the x. It is its own derivative.
Yeah.
Okay, what's the derivative of e to the negative x?
That's a good question. E
I'm
to
going to guess that it's the
same
negative x
thing. E to the
It's e to the negative x.
times negative
Chain
1.
rule. What's the derivative of the inside?
Negative 1.
Negative 1.
Negative 1.
yeah.
So in this case, it's negative e to the negative x is the derivative of that thing.
Why didn't you do the? Oh, you did.
We did.
Okay. Okay.
Or at least I thought you did. You told me the answer.
Yeah, I got it.
All right, let's try the next one. What's the derivative of this thing? E to the sine of x.
E to the sine of x times cosine of x.
E to the sine of x times the derivative of the inside, cosine of x.
Yeah.
All right, what's the derivative of this thing? E to the square root of 3x plus 2, or 3x plus 1.
It's going to be
It's gonna be
3x.
what's 3x?
E to the square root of 3x plus 1,
Just 3 plus 1, which cancels out.
which can be times the derivative of this thing.
Yeah.
Let's calculate that separately. I don't want to lose you.
Can
And just
you
write
do
it
to
off.
the 1/2?
3x plus 1 to the 1/2. Let's calculate that thing's derivative.
What 1/2?
It's going to be equal to bring the 1/2 out front.
Chain and then
And we have the 3x plus 1 to the minus 1/2 now.
And then just 3.
Times 3. Good. Or in other words, now I'm just going to rewrite that exact same thing. That's just 3 over 2 square roots of 3x plus 1. You see that?
Where do you get
3 in the top, 2 in the bottom. This now goes downstairs and becomes
Oh, because it's
a square root.
Wait, what are you doing with the 1/2?
So this 2 is right there.
Oh, I didn't, yeah.
The negative 1/2, bring it downstairs makes it a positive 1/2, which is a square root, and the 3 still upstairs.
Yeah,
Okay, so times that exact thing. 3 over 2 square roots of 3x plus 1. Not bad, right? Okay, let's try some hard ones. What's the derivative of 3 to the x? The derivative with respect to x of 3 to the x. What is that going to be?
3 to the x times
Which
natural log of
is
3 to the x times the natural log of whatever our base was. 3.
what rule's that?
That's this right here. What's the derivative with respect to x of a to the x? It's a to the x times natural log of a. Remember that this rule is just a special case of this rule. It's where the a happens to be an e. And so what is the natural log of e? 1.
Okay, yeah, that makes sense.
Okay, so what is the derivative with respect to x of 3 to the sine of x equal to?
A to the x, which is 3 to the sine of x.
3 to the sine of x.
Natural log of 3.
3 to the sine of x times the natural log of 3
So you want chain rule?
times cosine of x. Yeah, always and forever you have to chain rule.
Right.
Always and forever. Even when I'm asking you, what is the derivative of x squared with respect to x? When I say what is this, we are carrying out the chain rule. It is 2x times the derivative of the inside with respect to x. It's just that that keeps coming out 1.
That's right.
So we're always and forever doing the chain rule. Okay. One more.
Sure.
What is the derivative with respect to x of pi to the x squared equal to?
Pi to the x squared
times
times natural log of pi times 2.
2x.
Perfect. All right. That's probably messier than anything you'll get as a homework problem.
That is very strange.
Yeah, but these are actually kind of nice.
Yeah, it's not that bad. Okay. Let's do some integrals. So this time, let's do the integral from 0 to natural log of 2 of e to the 3x dx. What is that going to equal? Tell me where to start.
We have to
find
find
the
the
antiderivative,
antiderivative,
which is going to be e to the 3x plus c.
I know how to find the antiderivative of e to the u. The antiderivative of that is e to the u.
So you're saying you substitute 3?
You can do the u substitution. Maybe you can see the antiderivative right out the door. Can you see the antiderivative right out the door?
No.
The antiderivative right out the door is e to the 3x over 3. If you can't see that, then just do your u substitution. So let u equal 3x, right?
Right.
And then what does du equal?
3 times 1. What? 3 dx?
dx. Thank you. Okay. So now do your substitutions. Notice that we don't have a 3 here. I need 3 dx to get du. I don't have the 3 there.
Oh, so you divide.
So if I'm going to multiply a 3 there, I need to put a 1/3 out front.
Yeah.
You with me?
Yes.
Okay, and now this is equal to the integral from, we changed our bounds. We need to change our bounds now since we're doing u. Plug in 0 for x, what's u?
0.
And plug in plug in natural log of 2 for x, and what's u? 3 natural logs of 2.
So just
3 natural logs of 2, which is the same thing as the natural log of
2 to the power 3.
2 to the power 3, which is 8.
2 to the power. Oh, that's right.
Okay? I just know ahead that I'm going to want everything in the natural log, because we're going to be plugging into the exponential, and the e is going to cancel out the natural log.
Don't forget your 1/3.
So that's why I was combining everything. Thank you. So this is equal to the 1/3 right there, and now we just have e to the u du. And now what is the integral of e to the u?
E to the u.
E to the u. So this is 1/3 e to the u evaluated from 0 to natural log of 8. What is e to the natural log of 8? What is e to the natural log of 8?
8.
8.
What happened to your 3?
The 3 dx is my du.
Yeah.
Oh, so it's always there. Okay.
Okay, good?
Yeah.
Alright, so e to the natural log of 8, that's just 8. What's e to the 0? 0. Spelled funny. 1. E to the anything, or e to the 0 is 1. Anything to the power of 0 is 1. Yeah. It means I wrote a 1. That's all. Okay. And 8 minus 1 is 7. You all pass the class. Okay, 7/3. There it is.
Okay, we need to do more of those.
Alright, let's do another integral. So our next one is the integral from 0 to 2 pi halves, 0 to pi halves, of e to the sine of x times cosine of x dx. Okay. Obviously I need to do a u substitution. What do I want my u to be?
Sine of x.
Sine of x. So u equals sine of x. What does du equal?
Cosine of x. Wow, look at how that works.
dx. Okay. So we have du right here already. And here we have e to the u. So this goes straight to the integral of e to the u du. We got to change our bounds of integration. Because I'm no longer integrating with respect to x, doing it with u. So if x is 0, what's u?
X 0, u.
What's the sign of 0?
1. I don't know. I'm putting that.
What is the y coordinate at 0 degrees?
0.
0. And what's the sign of pi halves?
1.
Pi halves is 1/4 the circle.
1.
So for sine or cosine?
Sine.
0.
1.
1. The y coordinate at pi halves.
Oh, yeah.
1. Okay. And now, hard to get an easier one than that. What's that equal to? Plug in 1 for u, and what do I get?
E.
E. Plug in 0 for u, what do I get?
1.
1. So just e minus 1.
Where did you go?
He just did this.
Okay, sorry. So this is equal to e to the u, evaluate from 0 to 1, which is equal to e to the 1 minus e to the 0, which is equal to e minus 1. Okay.
Okay.
Is there a step you don't like?
How did you get?
He's just solving the definite integral.
So here to here is just calculating the integral. The integral of e to the u is e to the u. Evaluate from 0 to 1. Those were bounds of integration.
Okay.
Plug in 1 for u, minus what we get when we plug in 0 for u.
Yeah. Okay. I got it.
Okay. Any other questions? Okay, let's do another one. This one. Let's do the integral of 2 to the x dx. What on earth is that thing?
Okay, we do. It's.
Isn't it
Are we taking the antiderivative of that?
2 to the x? Over
We've already calculated, we already have a formula for the integral of a to the x dx.
Which is a to the x.
Which is a to the x
The
over the
natural
natural
log
log
of
of
a.
a.
So what is the integral of 2 to the x?
2 to the
It's
x.
2x over the natural log of 2.
2x times the natural log of 2.
Divided by natural log of 2.
It says
Right.
times up there.
We're doing
Oh, my God.
the integral of a to the x with respect to x. So in your derivatives, look, it's pretty straightforward. In your derivative, multiply by a natural log. In your integral, divide by a natural log.
Okay, that makes sense.
They're just counterparts to each other, right?
Yeah.
Okay.
Plus e.
Plus e. Good. All right, let's do another one. We are doing the integral of 2 to the sine of x times cosine of x dx.
So
u sine of
x, and then just.
Let's do our u substitution first.
So u is sine of x, du is that.
Yeah.
Okay. Now what?
It's going to be 2 to the
2 to the
u
u.
So 2 to the u
over the natural log of
over the natural log of
u. Why is
over the natural log of what?
2.
2, the base.
Why is that?
Oh, my bad.
Plus e.
You're right.
Let's see. 2 to the u
Yeah.
divided by natural log of our base.
Do we
Okay.
don't chain rule that? No.
No, this is already accounting for the chain rule.
Yeah, right.
Oh, in the formula. Right. Okay, yeah.
If you chain rule this derivative, when you take the derivative, you're going to get the cosine, which gives you that piece, and you're going to get a natural log of 2, which cancels out with that. So you're back to here.
Mm.
So take the derivative of that, you get that. Woo. Integral gives us an antiderivative. Who would have guessed? So you can always check your work. Always and forever remember that with integrals. Taking derivatives is way easier than taking integrals as a general rule. So if you go through all the work of calculating an integral and you're not sure, take a quick derivative.
Right.
Wasn't that just a formula?
Yeah, you just plugged into a formula.
Okay. Yeah, that's all I need.
That's all you need is just your formulas, right? That's how you thrive in physics. Alright, let's get a little bit more space. Okay, here's a cool one. What is the derivative with respect to x? I'm pretty sure this one's going to be on your test. Of x to the x.
Yeah.
Yeah, that will be a test problem for sure.
That's just one.
Oh, by the way, test next week. Don't forget that.
That's right. Yep.
So
That's just one
That makes no sense.
of x to the x.
No, it's not.
2x minus
No, it's not.
it's
This function x to the x. Let's think about what this thing looks like, just to guide our intuition.
you put in one.
Plug in 0, 0 to the 0. In this function, we're going to treat it as 1. Okay. Plug in 1.
You get 1.
You get 1.
Like two.
Plug in 2, what do you get?
4.
4. Let's say 4. I'm not sure if that thing throws off. We'll just say for positive numbers. Okay. When you plug in 3, what do you get?
9. Or,
No, that's 3 squared.
yeah, you get
27.
27.
You get 27.
yeah.
Oh.
So when you plug in 3, you're already caught up at 27. When you plug in 10, what do you get?
Million.
That's a big number.
100,000.
10 trillion or something.
That's a large number. I'm not sure.
You know the number. It has 10 zeros.
I
Do not know the number.
I do not.
Yeah,
know.
you do.
10 million. 10 billion.
10 billion. It's just 10 billion.
Oh, that's obvious.
Okay.
10 to the 10. 10 billion. Yeah, you can do that. So if you just go over to 10, you're already up 10 billion.
That's a. Yeah.
This function grows stupid fast. And you're saying its slope is 1?
At 1 it is.
So what is the slope of this function? We're looking for its derivative. The thing that gives us the slope at any point.
Okay. Yeah.
So when you come over here at 10, its slope is going to be stupid big.
Okay. Alright. It's going to be x to the x times the natural log of x. If we do the first substitution.
It's going to
Wait,
be...
does that work? I'm doing the first theorem that we have, the first substitution.
You're saying here?
Yeah.
So you're saying that, so you're saying take its derivative, and this is going to be x to the x times the natural log of x.
Yeah.
No, that doesn't work.
Okay.
Because
The a is
a is a variable here. It's not a constant.
Okay.
Notice that your base is a variable and your exponent is a variable. The same way that calculating the derivative of 2 to the x is very different from calculating x squared. Those are drastically different functions. And so it's also drastically different from this x to the x. Okay, so how on earth are we going to take the derivative of this thing? You should be getting a little bit stuck.
I don't know.
And what should we always and forever do when we get stuck? If you're getting stuck with exponentials, rewrite it in terms of e. If you're getting stuck with logarithms, rewrite it in terms of natural log. Always and forever, that's what we do. Anytime we get stuck with these things.
Yeah, but it's not a to the x.
So let's do the substitution.
It's not.
This is true for any number a and for any number x.
So, and that top one's not.
This is how you calculate the derivative of a constant to a variable.
Oh, so. A
This
is like
replaces x here with b. It's just if you have a to the b, it's the exact same thing as this. It's just another way of rewriting the exact same thing.
That's different then. Okay, so you just do.
So this is the same thing as the derivative with respect to x of e to the x times natural log of x.
Okay.
Good? And now, how do we calculate the derivative of that thing?
E to the x.
That would be e to the x times natural log of x times the.
So it'll be e to the x times natural log of x
Times
times the derivative of the inside. So what's the derivative of x times natural log of x? Let's calculate that separately.
1 over x. which
Derivative with respect to x of x times natural log of x is equal to what?
Natural log, I want to say. I don't know. Natural log of x is 1 over the x, and then the x is x to the 1.
What is a derivative of a product?
Product of the three.
Product of the, wait, no.
No!
No, it's not.
Going all the way back to our basic derivative rules.
It's
The
The
first
derivative
times
of-
the
it's the u
second.
prime times the v times the v prime times the u.
So yeah, you can do the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Is that right?
Yeah, so if you think about that as your u and that is your v,
So
then u prime
u prime, which is just 1,
times v
v, which is
plus v prime is
x over 1, or
1 over x times x is
uh,
1.
1. 1 over x times x is 1. It's why you're saying 1 to begin with.
Oh, really? Okay.
Okay, so times natural log of x plus 1. There we go. Not too bad. Shockingly simple problem. That's something that you can get stuck on forever until one little substitution clears it all up. We could have also solved this another way. Here's the way I solved it, because I remember getting this problem when I was in school. I did y was equal to x to the x, then just take the natural log of both sides. Natural log of y is equal to natural log of x to the x, bring the x out front. Calculate my derivative, so 1 over y times y prime is equal to the derivative of this, is we already calculated right there, natural log of x plus 1. And then move your y to the other side. So y prime is equal to y, which was x to the x times natural log
So
of x plus 1. And notice that this portion, x to the x, is the exact same thing as this. So this is equal to x to the x times natural log of x plus 1.
So why? Where did you get that y prime from?
What is the derivative of the natural log of y?
Which is
1
just
over y
1 over y.
times
Oh.
the derivative of y with respect to x.
Okay.
So that's how I solved it, but the way the author intended the problem to be solved was this substitution. And doing the substitution is a good idea. When you get stuck on an exponent, substitute it in terms of e, and that usually makes it clear how to do things.
Do the y one because it's more ingrained in memory.
Well, whatever works, but be ready for it on the test. Okay, let's see, derivative of this thing. So, what is the derivative with respect to x of the log base 10 of 3x plus 1? Looking for its derivative now.
I'm just gonna guess that we are supposed to substitute for natural log.
Yeah, so that'll be.
You could if you wanted. We already, sorry, this wasn't, okay. Kind of just threw this question on you guys. Remember that I hate how the author covers all this. And he gives all sorts of weird definitions. So he gives this as an example problem, but I proved this derivative rule last week.
Yeah.
So we proved that last week, but you probably didn't have any homework problems having you calculate derivatives of logarithms. So our formula is actually over here, which we proved last week. So it's just 1 over x times natural log of your base. And then remember your chain rule. So it's just 1 over whatever our x is, 3x plus 1, times the natural log of our base, 10, times, oh sorry, not times natural log of your base, divided by natural log of your base. So times 1 over natural log of 10.
Times 3.
Times 3. So this will be equal to 3 over natural log of 10 times 3x plus 1.
So log base a x is 1 over
Log
x
base a of x, when you calculate its derivative, is
equals
1 over the x, whatever that is,
which we had, okay.
times the or divided by
1
natural
over
log
natural
of whatever your base was.
and then chain rule, right?
Yeah, and then just chain rule. Always in forever chain rule. Okay, and then our last one was this integral. Now, cursive space, let's do this integral. We're doing the integral of log base 2 of x over x dx.
Is this quotient rule now?
No, this is integral, it's not a derivative.
Oh yeah, so we
If
need
you were calculating the derivative of that, it would be a quotient rule.
well we need to do the antiderivative of that.
Well, you gotta do a u substitution on this now.
Yeah.
So u is log base 2 times x.
But then what's the derivative of this thing gonna be?
I don't know. That is what?
So if we let u be log base 2 of x, what is du? Of course. What's du equal to?
u equals oh that's what you're saying.
Du, yeah.
1 over oh shoot. Wait, 1 over x.
1 over x times log.
Times 1 over the natural log of 2.
2, good.
Yeah.
Oh, from
My
that
bad.
rule?
No.
Okay.
Right, so now, notice that I don't have a natural log of 2 in the basement here. Well, don't forget our dx, right? So notice I have a dx in the top already, and I have an x in the bottom, but I don't have this natural log of 2 in the bottom. So I need to multiply top and bottom by natural log of 2. So we're going to get a natural log of 2 times the integral of log base 2 of x, that's just u, times, now we just have du. Because our du gets us the 1 over x, gets us the dx, and then the natural log of 2 in our du cancels out with this one. You see it all? Okay. And now, what is the integral of u with respect to u?
U with respect to u.
It's u
There's a throwback. It's what?
squared over 2.
Just u squared over 2. So this is just equal to
U over u.
natural log of 2 times
U squared over 2.
u squared over 2. The integral of u,
Oh,
with respect to
duh.
u.
Oh my, okay.
u to the 1, if that's helping you see it,
Okay, there we go.
plus some constant,
Yeah.
which is
6.
cursive space there, accidentally rewrite some of our du. Our du was 1 over x times 1 over natural log of 2 times dx. Okay, back to over here, this is equal to natural log of 2 times, what was our u? Log base 2 of x.
Log base 2 of x.
Squared over 2. Now, in the answer that the author gives you, everything you guys did was perfectly acceptable. In the answer that the author is going to give you on these logarithm problems, it's always going to be expressed in terms of natural log.
Oh, okay.
So when you look at the answer, what is log base 2 of x equal to? In terms of natural log, when you look at our change of base formula, or you can just look at this one.
It's the natural log of x.
X.
Natural log of x over natural log of 2. So now when I plug that in there, this is going to be equal to, we'll have natural log of 2 over 2, accounting for our two constants here. That was a 2. Times log base 2 of x is this thing squared. So that's going to be the natural log of x squared times the natural log of 2 squared.
Where did you get that to?
So doing this substitution for this.
Okay. Shouldn't that be on top of a divided by?
So that whole thing squared is this. That 2 is this 2. I just moved it over here with that.
Can you do that?
Yes. 1/3 times 3 is the exact same thing as 3 over 3.
Yeah.
you could put the denominator, and then leave the 1 here, 1 times that. I can move my denominator to whichever term I want if we're multiplying.
Yeah.
Okay, so now this is equal to, notice we have a log base 2 squared in the denominator, a log base 2 there, one of those will cancel. And so you'll get natural log of x squared all over 2 times the natural log of 2. So this is the answer you'd see in your book, not this. For that reason, it is typically better, rather than the way we did it, which is perfectly fine, there's nothing wrong with it, it's better if you have a logarithm starting out, do your substitution in the beginning. And so log base 2 of x, this is now the integral of that's natural log of x over natural log of 2 times 1 over x dx. This is the same as that, right?
Yeah.
Doing our substitution early on.
Yeah.
Well,
And
that's
now, let's pull our natural log of 2 out. And so this is the integral of natural log, 1 over natural log of 2.
Yeah.
1 over natural log of 2 times natural log of x dx all over x. Put the dx right there. And now if we let u be natural log of x, du is 1 over x dx.
1 over x. So that's way
Way simpler.
That's way
Right, so this is now just equal to the integral of u du, which is equal to u squared over 2. Oh, forgot our coefficient here. 1 over natural log of 2. And now u is natural log of x. So that's going to be equal to natural log of x squared, u squared, all over 2 times the natural log of 2, 2 times natural log of 2. It's good practice to put the natural log after if you just have a number. And you get the same thing. So it's a cleaner way to do it. So if you see the logs, as a general rule, just replace them with natural logs and you'll be better off.
Good.
Okay, so there is our exponents. Now, differential equations.
Yeah.
Okay, so for differential equations, a differential equation is an equation where how the system is changing depends upon the current state of the system. So an example where we would use a differential equation to model would be something like population growth. If we look how fast people are growing in our town, one of the things it depends upon is how many people are actually in our town.
Yeah.
Right?
Yeah.
Yeah.
It's a big difference if a city of 10,000 people is growing by 10,000 people per year versus a city of 1 trillion people growing by 10,000 people per year. Those are drastically different scenarios, right? You would expect the more people there are, the more the population grows in terms of number of people.
Yeah.
Or you can think about it as rabbits in a field. Or you can think about it as bacteria in a petri dish.
Yeah.
The rate at which they grow depends upon the actual bacteria. Or we can also look at things somehow shrinking. Imagine that I heat up a cup of coffee in our room now. What's going to happen to that cup of coffee?
It's going to expand.
I heat up the room, so now I got a hot cup of coffee. I come back after an hour and I taste the coffee. What happened?
It cooled down.
It cooled down. And if I were to take my coffee to Antarctica, does it cool down faster or slower than me keeping my coffee in here?
Faster.
That's slow.
Slower. What's faster?
The colder I put it in, the faster it drops down. And so the temperature, when something's really hot, it cools down quickly, but then it slows down the rate at which it cools down. And so how quickly it cools down depends upon how hot it is compared to the environment we're in.
Yeah.
Interesting. Okay.
Right? If I take my cup of coffee and I go put it on the surface
Yeah.
of the sun, it's no longer cooling down. It's heating up.
Yeah.
Theoretically, yeah.
But the point is, if I have the hotter my coffee is compared to this room, the faster it cools down. So if we looked at the temperature of my coffee, it would go like this. Here's the temperature of the room. The temperature of my coffee over time would look something like this.
Well, and the room would heat up a little bit too.
Yeah, but we're going to ignore that. That's negligible, the amount of heat the coffee contributes to the room. I bring my hot cup of coffee in and go stare at the thermostat. Right?
Yeah.
So the temperature of a system depends upon the current temperature of the system, how fast the temperature drops.
Yeah.
And so when it's really hot, it starts cooling down really fast and it slows down the rate at which it cools down. And it cools down less and less and less until it gradually gets right at your room temperature.
It will never cross that line, right?
It will in a real system.
Because everything adds to 1.
Well, no, because it's real world and you're talking about jiggling atoms and whatever. So within some margin of error, yes, because our margin of error will eventually get in that margin of error in a real system.
Yeah.
But it can always get half that.
No, you can't always get half that. The reason you can't always get half that is you can't always get half an atom. If I have 100 atoms in this room, I can't keep halving them. I can half it down to 50 atoms, and then 25. And then I can't get 12 and a half atoms. I can get 13, or I can get 12. I can't get 12 and a half. So no, there's physical limitations on the system and all sorts of randomness to the system, so no, it will eventually get there.
But will it keep flattening out?
It will eventually just get so close to it that for real world purposes, the difference between that and that is no longer something we can talk about meaningfully. But it doesn't matter. It gets close enough. It gets arbitrarily close.
Alright.
It gets so close you can't tell the difference. We'll say that. So, looking at differential equation. So I've got y here, and it's going to be equal to some function that changes with time. Is a typical way we first model this. Something like y could be modeling your population, or it could be modeling the temperature of my coffee. Something that's changing with respect to time. What's going to happen is, well, so if f or y is equal to some function in terms of time, we're going to use a special variable y naught to talk about f at 0. So if we were modeling population over time, something like that. Here's a population over time of some town. Y naught is just whatever the starting population is.
Y-intercept.
Yeah. Or we could be talking about your investment. There's another thing. The more money you have invested, the faster it grows. And so the Y naught would be your initial investment. So it's your town's starting population. It's your initial investment. It's your coffee when you first bring it into the room. The temperature of your coffee. Whatever it is, it's the initial condition of your system. Whatever it starts out at time t equal to 0. So y is a function that depends upon t. Y naught is a symbol we're going to use for when you plug 0 into our function.
Okay.
And if the derivative of y with respect to t is proportional to y. So it's equal to y times some constant. It's proportional to y. If how the system is changing is proportional to the state of the system itself, then y is equal to y naught times e to the kt. Now we're going to really quick derive this and prove it, but here's the equation that you're going to be using over and over again. And I want you to see how differential equations naturally show up in the real world.
And y naught is just the base state.
Y naught is just what we're going to use for when you pass 0 into your function, just whatever your initial is.
Okay.
But so let's think about this. I'm modeling the change in population or whatever it is. And I'm looking at its change. So I'm just starting out with the assumption that however it's changing is somehow proportional to how many people there are. Right?
Yeah.
So now, I'm just going to solve this equation. I'm going to solve it for y.
Okay.
Now the problem is that I have a dy dt there and a y there. I need to somehow integrate this thing to cancel out my derivative. But how on earth do I integrate that thing?
Take the integral.
Well, let's try something. So now I've got dy is equal to k times y dt. So I could have done that, right? And now I could try integrating both sides. What's the problem that I have?
Yeah, then great.
My y shows up over here. How can I integrate y with respect to t?
Constant.
That's the wrong variable. Y is not a constant. Y is a variable. K is a constant. We don't have to worry about that. Y is a variable.
Yeah.
I know how to integrate y with respect to y. And so I want to get my y on this side.
Can you do that before?
Yes. So that's exactly what we're going to do. I'm going to multiply both sides by dt to get my dt over there and divide both sides by y. And so I'm going to get dy over y is equal to k times dt.
You divide by y.
Multiply both sides by dt, divide both sides by y. So I move my y over here and my dt up here.
Yeah.
Oh, you're just using like a differential.
Yeah. Now we can integrate both sides. Now I know how to integrate 1 over y with respect to y. What is the integral of 1 over y with respect to y?
You mean 1.
It's your.
What is the integral of 1 over x with respect to x?
It's the natural log of
Okay,
x.
you pull it.
Just natural log of x.
Yeah.
Yeah. So what's the integral of dy over y?
It's the natural log of
Natural
y.
log of y.
Just natural log of y is equal to, what's the integral of k with respect to t? K is just constant.
It's gonna be k.
That's the
Wait.
anti.
K to the power, or
No, it's just kt.
K2.
It's just k times t.
Yeah.
Take the derivative of that with respect to t. What do you get? K.
Yeah.
Now when we take that integral, it would have been plus a constant, and when we take this integral, it would have been plus a constant.
Yeah.
Put both those constants on the same side, and it's still just plus some constant c.
Assuming 1's greater.
No, it doesn't matter. C could be a negative number here. If here it was plus 10, and if here it was plus 2, subtract the 10 over here, now it's minus 8.
Yeah, minus some constant.
Or plus negative 8. The constant could be a negative number.
Okay, yeah.
So it could be positive, it could be negative, it could be any constant. Positive or negative, we don't care.
Okay.
Alright, so now we need to figure out what y is.
Right.
So how do I get the y by itself?
Take
Raise
the
it.
log. Take the log.
No.
Take the exponential to cancel out the log. So then e to the natural log of y is going to be equal to e to this whole thing.
Oh, it's so weird. That's right. Okay.
Mm-hmm.
If that is equal to that, then e to that is equal to e to that.
Yeah.
And now what is e to the natural log of y?
Wow.
Just y. E's and natural logs cancel out each other. Is equal to e to the k times t. When you add exponents, that's the same as multiplying terms.
Yeah. Well, c times e.
Which is just a constant, isn't it?
X to the 2 plus 1 is the same thing as x squared times x to the 1.
Wait, is it e to the c just a constant?
Yeah, c is just constant, e is just constant, so e to the c, that's just constant. So we're going to call that whole constant capital A, and so this is equal to a times e to the kt. You with me so far?
Yeah.
Okay.
So there's a pretty standard equation that you'll see all the time. Y is equal to a times e to the kt. Now, what happens when t is 0?
You get
Let's handle that special case.
It's just
If
a.
I have y, what is y at time 0? So y, when we plug in 0 for y, what do we get?
It's-
We get a times e to the k times 0.
Which is going to be a, because e to the 0.
Right, what's k times 0?
0.
0.
What's e to the 0?
1.
What's a times 1?
A.
1. A.
A.
A. And so this a is what we get when we plug in 0 for t. And so we mark that a with a y naught. And so we use y sub 0, or y naught is what I'm going to call that.
1.
So it's whatever your y was at time 0. That's what your a was. What is that constant? It's whatever your y is when you plug in 0 for t. If this was population growth, that a represents your starting population. If you were investing your money into something, that a represents your initial amount.
Okay.
Yeah.
And that's, I mean, the way you see it, how do they typically do it? The amount you have, well, no, there'd be no there. Similar idea, but I don't want to go too far off. Okay, so there we go. Here is our equation that we use when we have this scenario. When our change in our function is proportional to the function itself.
Okay.
Then here's the equation we use. Y is equal to y naught times e to the kt. Good?
Yeah.
Now, the types of equations that we're talking about are differential equations. They don't necessarily have to be this clean. So now I'm going to show you how we can solve any differential equation when the derivative of y with respect to x is equal to some function that has both x's and y's mixed together in it. Now we can only do this in the special case that I can somehow collect all my x's together and collect all my y's together and view it as a product of all my x terms times all my y terms. If I can get my derivative represented this way, So now, dy dx, looking at this, multiply both sides by dx, divide both sides by h of y, gives me this. I can take the integral to calculate those. That's a lot of notation, but I think when you see examples, it will help clear it all up. So let's calculate some of these now and get some concrete examples. So I'm starting with this one. I know that dy dx is equal to y plus 1 times e to the x. Now I can't just integrate that thing with respect to x because I have a y over there. So I somehow need to get all my y's with the dy term and all my x's with the dx term. I need to be able to somehow separate them. And that's why they're called separable differential equations. So this over here is like our h of y. This over here is like our g of x.
Okay.
So multiply both sides by d of x to get my dx over there. And divide both sides by whatever my y one is over here. So I'm going to get d over y, y plus 1, is equal to e to the x dx. You with me? And now I can integrate. And now what's the integral of 1 over y plus 1 with respect to y?
1 over y. What?
Is
What is the integral of 1 over x with respect to x equal to?
Natural log.
Natural log of x. What is the integral of 1 over y plus 1 with respect to y equal to?
Natural log of y plus 1.
Natural log of y plus 1.
Oh.
What's the integral of e to the x?
dx.
And then plus our constants. Combine both our constants from both our integrals on the same side. So what did we do? When you have dy dx is equal to some function that has x's and y's together in it, try and view it as dy dx equals some function of x's times some function of y's. Then divide the y's over under your dy and multiply the dx over here. And then integrate. That's your general strategy. Let's try one a little bit more convoluted. So this time we've got this. Y times x plus 1 times dy dx is equal to x times y squared plus 1.
Okay.
I want to try and separate this, so I want to try and shove all my x's on the right hand side and all my y's on the left. Right?
Yeah.
So this is the same thing as, let's bring my y's over here, so I got to divide this over here. So we're going to keep this y on this side. I'm going to divide that by this y term. We still are going to keep the dy over here. And so I moved all my y terms on this side of the equation. Now I'm going to move all my x terms on this side of the equation. So we already have an x over there. When I move this over, that's dividing both sides by x plus 1. So that's going to put the x plus 1 down here. And then multiply the dx to both sides, puts my dx right here. You see that? Just separating my x's and my y's onto either side of the equation. And then we can calculate the integral. Okay? So what is this integral?
Y over y. Isn't that just natural log?
Are you doing it all in your head? You may need to do a u substitution. I don't know if you'll be able to do it all in your head, but you can do it all in your head if you can. So what is our u going to be?
Our u is y squared plus 1.
U is going to be y squared plus 1. So what's du going to be?
Du is 2y. d-a-y.
2y dy. Okay, so we have our y dy. We need a 2.
2 to the other side of the integral.
So perfect. Put a 2 up here, and then we can put a 1/2 out front. Right?
What?
A 1/2.
Oh, yeah.
To cancel out the 2. So we've got 2y dy all over y squared plus 1.
Yeah.
So calculating just that portion of the integral, let's calculate that. So that now is the integral. We have 1/2 of du over u,
Yeah.
which is equal to,
You do this every
Natural log of u.
yeah, 1/2 the natural log of u. Let's remember what our u is, y squared plus 1,
y squared plus 1, yeah.
plus some constant. We'll call it C1. Okay?
Okay.
So we calculated the integral of this half. Now we got to calculate the integral of this half.
You just broke up the integral.
Well, no. We have this integral is equal to this integral. So we calculate this integral. That's this thing. I can go plug that in.
So why do we need the other one?
Because I've got to solve what this thing equals. I can't just integrate one side and not integrate the other side.
Yeah.
Okay,
What you do to one side, you have to do to the other.
Okay, alright.
Alright, so now,
That
here's
is-
another good one for you guys' test.
That's a U sub right there.
What's the integral of x over x plus 1 dx?
We U sub x plus 1.
If you do u is equal to x plus 1, what's du equal to?
Du is equal to 1.
It's just equal to dx, right?
Yeah.
Yeah.
And so now this is equal to
Is that
the
wrong?
integral of x over u du.
Then you can't do that, right?
Well,
What do we do?
Are we led astray? Is that?
Sure. Oh no, it's not.
Let's just U substitute the x.
Let's just u substitute the x. What does x equal?
U.
X does not equal u.
Well, not U.
if you
U equals x plus 1. What does x equal?
Oh,
the
we're
minus
duh. You move it on the other side.
What?
Or U minus 1. X equals
U
U
minus one.
minus 1.
Okay, so
We've
this is
done
equal
this
to u minus
before.
1. We have done this before. Very easy. Which is equal to the integral now of
The
natural log.
no,
One.
No.
These
What?
cancel out, don't they?
no.
No, they don't. My bad.
1 over U, which is natural log.
Now it's not just 1 over u.
Look, you
What is u minus 1 over u equal to?
You cancel out the U's and then you
You
have
don't-
net
you
minus
don't
1
cancel
over
out.
U.
5 minus 1
Oh,
over
right.
5 is not equal to negative 1.
Right.
It's equal to 4
Well,
fifths.
It's not equal to negative 1, but negative 1 over 5. Because.
No, it's not. What?
Okay.
Negative 1 over 5 is minus 1 fifth. That is equal to 4 fifths.
Weird.
What do we do with this?
We,
The reason I'm going to give you this one on your test is because this is simple algebra. And it's what you guys are awful at.
yeah, it looks like it's a wrap.
You can take the 1 over u out.
You can't pull that out of the integral. We have to integrate it.
Is it there some?
Oh, yeah, you can use it like this if you want. Okay, that's 1 over u times u minus 1. That helps.
Are we taking the derivative of that? But
Take the integral.
We got to calculate the integral of u minus 1 over u.
so can we use the power rule and just add 1 or no?
I feel like I feel really stupid.
I thought I could help.
That could.
Now what should we do?
You can you? I guess you can't take the 1 over u out from the integral.
Okay, alright.
You could view 1
Could we do the quotient?
one.
is that not equal to 1 minus 1 over u?
It is. That's exactly what it's equal to. Distribute it through if you want to think about it that way. U over u is 1 minus 1 over u.
That's what I said. I said you have your
You said
U's
something
cancel
about a
out, and
chain
then
rule.
It's left with 1 over u.
We didn't have u's cancel out.
Yeah,
They're
I
still
said-
there.
I said it really stupidly, but
Well, I can't decode whatever you're saying.
It's a math teacher, not a Mike.
Okay, and so now we got that.
okay, that's awesome. Cause
Okay, now how do we calculate the integral?
flip u up, which is just negative.
Do not.
Don't mess with that u. It's where you want it. The integral of the sum of two terms, remember, a difference is really a sum,
The integral of each.
is the integral of each of them. So what's the integral of 1?
U.
U.
And the integral of 1 over u.
What's the integral of 1 over u?
The natural log of u.
Natural log.
After we got there.
Holy.
We got there.
Okay. That was pretty fun.
That was pretty fun. Well, we're not done yet.
Well,
We still got u's, we need x's.
okay, plug.
So this is equal to x plus 1 minus natural log of x plus 1. Okay, so going all the way back, we calculate the left-hand side, we got this. Calculate the right-hand side, we got this. And so we get 1/2 natural log. You guys lost complete track of what we were doing. is equal to that thing, x plus 1 minus natural log of x plus 1.
Plus C.
And then we have this constant and that constant combined together as some constant, we'll call it C2. Okay, my answer is still stupid. I have one stupid thing left in there that I should not have written. Find my stupid.
X.
Well, it was worth a shot.
Plus
There's
1.
some x's in there. The plus 1. What is 1? A constant. What's a constant plus a constant?
The constant.
A constant. So that plus 1 is stupid. And so just say, okay, we'll call all those constants together C now. So when it's all said and done, all your constants are collected together. And any other constants that show up are just stupid.
Got it.
So what about your 1/2 over there? Never
That's
added.
That is multiplied. It's not adding a constant. All the constants we add together, just collect them all together.
Yeah.
Constants are like terms. Collect all your like term constants together under one constant.
Just
That make sense?
collecting your coins.
Alright, so there's the hardest problem. Now, some story problems, the cool problems. The problems that will be like the stuff we do in physics.
Alright.
Oh, come on. We're not even 2 hours into class.
Yeah, but we're 18 hours through the day.
Probably.
Alright, example 3. These ones, it would help if you pull out your book and read the examples as we go. Because one of the hard things I think you may get stuck on is extracting the information out of the story problem.
Zach, do you have a USB-C charger?
I have not on me.
Dang. We're on that now.
Alright, so 3 story problems and then we're done forever, right? Done with the class. So hang in there for 3 more problems. You can do it.
Well, then there's homework.
Yeah, but for lecture-wise. Okay, so example 3. The biomass of a yeast culture in an experiment is initially 29 grams. So I am starting out with 29 grams of yeast. With me so far?
Yeah.
After 30 minutes, the mass is 37 grams. So maybe think about it like this. So our y, our yeast, is some function in terms of time t. I know that at 0, how many grams did I start out with?
What page is that on?
Well, yeah.
29 grams. We are on page 396. Example 3.
Okay.
You find it?
Yeah, it's initially 29 grams.
So I start out with 29 grams. And then I'm told after how much time?
30 minutes.
30 minutes.
After 30 minutes, I have how many grams?
37.
37 grams. So whatever is going on, my yeast is growing in some culture in a lab.
Yeah.
Some bacteria, right? You still searching for it?
396, you said? I'm on. What?
Page 396 in terms of the book, not the PDF.
411 is what I have. I don't know what
For what?
So there's the PDF page, which is what the PDF says you're on, and then there's the book, the number that actually shows on the book.
Oh.
And so in terms of the book numbers page, it's 396, not the page number in the PDF.
Okay.
That's the same reason.
Alright.
Example 3. You find it?
Almost. Yeah, okay. The yeast culture is an experiment.
All right, yes. So let's get your brain caught up again. So y here is going to be our function that tells us how much yeast we have.
Okay.
So it's some function in terms of time. I don't know what function it is in terms of time, but it's some function in terms of time.
Okay.
I know that at time 0, we have 29 grams.
Okay.
And I know at 30 minutes, we have 37 grams.
Okay.
There's my information so far. What am I trying to figure out?
We're trying to figure out how long it will take for the mass to double.
How long will it take for the mass to double from its initial value? So here I am, I'm sitting in a lab. I know I start out with 29 grams. I come back after 30 minutes, I've only got 37 grams. I don't want to keep checking on this thing. I just want to come get it when it has exactly double what I started with, or when there's 58 grams in there. So the question is, when should I come back and get my yeast? So I'm looking for the time that makes so that f of t, I'm looking for some time called t1, such that f of t is equal to 58 grams. Double what we started with. 58, 2 times 29 is where that number came from. You with me? Okay. So, this is going to be some growth function like this. So I know that my function y is going to be of the form y naught times e to the kt.
How do you know that?
Because my yeast is something that how fast it grows depends upon how much there currently is. So in other words, the big assumption behind this problem is whatever my function is, that the derivative of y with respect to t is somehow some constant times y. What is the derivative of y with respect to t? It's how y is changing with respect to time. We're assuming that the growth of my function depends upon what my current population is. It's somehow proportional to it. In other words, if you double my population, I'm assuming that doubles the rate at which the bacteria reproduces.
Okay. Alright.
Does that make sense?
Yeah.
So here's our big assumption in the problem. So now working with this, move the y over here and the dt over there. So then dy over y is equal to k times dt. Integrate both sides. Over here we get a natural log of y is equal to, over here we get a k times t, and then collect the two constants together plus c.
Where do you get k?
K is just, it's proportional to it. I know that if I double my population, I double my growth.
Yeah.
But I don't know like the reproduction rate.
Yeah.
So K is like the reproduction rate. I don't know how fast that bacteria is splitting. I'm just assuming that if I use twice as much bacteria, it would grow twice as fast.
Okay.
So I'm assuming that the change in the population is proportional to the population. It's the population times some constant. I have no clue what that constant is. We're going to have to figure that out.
Alright.
So, you good with going from here to here?
Yeah.
Now if this is equal to this, then e to that exponent is equal to e to that exponent.
You would say again, Mark?
If natural log of y is equal to k times t plus c,
Yeah.
then e to the natural log of y is equal to e to the k times t plus c.
Yeah.
All right, and now this is equal to e to an exponent plus an exponent is the same thing as e, I'm going to do the c first, times e to the kt. Or, oh, k times t, sorry. When you add exponents, that's the same thing as multiplying terms.
Right.
Yeah.
Okay, so now what is e to the natural log of y of y?
One.
E and natural log just cancel out each other all the way back here.
Yeah. Sorry.
No, that's fine. Keep thinking it through. It's going to take a couple times until it clicks, and then it just feels obvious.
Yeah.
And that's just the way these things go. So y is equal to e to the c. E is just a number, c is just a number. That's just another constant. I'm just going to call that whole constant a, whatever it is,
Okay.
times e to the kt. Now notice that whatever this a is, it's what I get at time 0. If I plug in 0 for t, k times 0 is
Sure.
0. E to the 0 is
It's just a.
1. So a times 1 is just a. So whatever that a is, it's whatever my y was at time 0. Which is what we mean by the symbol y naught. It's a stand-in for whatever the value was at time 0.
Okay.
So the way the equation will be shown is y is equal to y naught times e to the kt. You with me?
Yeah.
Now in our special circumstance, we know that y naught is equal to what? How many grams did we start out with? How much bacteria? 29 grams, so 29. Right? Furthermore, I know after 30 minutes we had 37 grams. So I know we have 37 grams, or y naught now we know is 29. After 30 minutes, when I plug in 30 to this equation,
Okay.
then it has to come out 37 here.
29 is the base. Okay.
29 was our initial one at time 0. Notice when I plug in 0 to this equation, what do I get? If I replace that with 0,
You get 20.
then I just get 29. 29 is what we get times 0.
Yeah.
So 29 was our initial amount. I know after 30 minutes, I have 37 grams. That's this information.
Mm-hmm.
And now I can use that to solve for k. We'll call k our reproductive rate, whatever we want to call it. I can't remember what it's called there. It's something like the constant of growth or something.
Yeah.
So now we can solve for k. So first off, divide both sides by 29. And so now I get 37 over 29 is equal to e to the k times 30.
We don't know what E is though.
E is just a number, like pi.
Oh,
E is
that's
2.7 da 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 da. So we do know what it is. Just some number.
Okay.
With me?
Mhm.
So now take the natural logs of both sides. Then the natural log of this is equal to the natural log of this. What is the natural log of e to anything?
It's just that.
Just that thing. So then I get natural log of 37 over 29 is equal to k times 30.
Divide by 30.
Divide both sides by 30, and I get k is equal to the natural log of 37 over 29 divided by 30, which will come out approximately 1 over 30 times natural log of 0.0081118. So there's our k.
Yeah.
So now we have that number. So now our equation, whatever it looks like, our equation is of the form y is equal to 29 times e to the kt, but we know what the k is now. It's just this number. I'm just not going to write it in.
Yeah.
So now for any t you give me, I get one and only one output. I can figure it out now.
Figure out when it's double.
So now we got to figure out when it's doubled. So now I got to find the t such that 58 is equal to 29 times e to the kt. I need to find the t that makes that true.
Yeah.
And it's a very similar process. What's 58 divided by 29? 2. That's how we got 58. It's double 29. So then 2 is going to be equal to e to the kt. Take the natural log of both sides. So I get natural log of 2 is equal to kt. So I get t is equal to natural log of 2 divided by k, where k is that number. And so it comes out to about 85. So we already waited 30 minutes, right?
Yeah.
So you gotta wait 55 more minutes.
So we got to wait 55 more minutes for the population to reach the doubling point. Because 85 minutes is how long it takes to double from the start.
Yeah.
We knew after 30 minutes is at 37 grams, so we were trying to figure out how much longer do I have to wait before this population reaches its doubling point.
Okay.
And so the answer to the question is 55 minutes, I think.
Wow.
That's how much longer we need to wait until the population is doubled from where it started.
It's
Does it-
85.
85 is-
Oh, they just want 80, they want, how long did you have to wait from the start? So, okay, they just want 85 minutes. They just want that number. But either way, it's the same thing. 85 minutes from the start or 55 more minutes, assuming we already waited 30.
And where did you get 55 from? Subtracting 30?
Subtracting 30. I was assuming we already waited 30 minutes.
Okay.
And so 55 more minutes is when the population doubles. Because it doubles at time, 85 minutes, from when we started. Make sense?
Yeah.
Alright. So these are the types of problems that I'm more interested in you knowing how to do. And that's the type of thinking that shows up more in like a physics type problem. So let's do another one.
Can I go use the bathroom?
Yep. Start reading example 4 to me.
One model for the way diseases die out. Assume that the rate dy dt of which the number of infected people changes is proportional to the number of lives.
Okay, so we've got some sort of disease, dy dt, we are assuming it's proportional to y somehow.
The number of people cured is proportional to the number y that are infected with the disease. Suppose that in the course of any given year, the number of cases of the disease is reduced by 20%. If there are 10,000 cases today, how many years will it take to reduce the number to 1,000?
Perfect. So at time 0, we're starting right now today, there are 10,000 people who have this disease.
Okay.
How fast we are eradicating the disease is proportional to how many people have the disease.
It's 10,000.
Well, it's just this proportionality. We're assuming this relationship. This relationship is always and forever what gives us this equation. This equation follows from this relationship. If this is true, solve it, it spits out this.
Okay.
Okay, so now we are assuming that every year we eradicate 20% of the disease. So after 1 year, how many people still have the disease? If we got rid of 20% of diseased people after 1 year?
8,000.
8,000. After 2 years, how many people have the disease?
20% of 8.
13? No, 14?
20% of 8 is going to be 1.6. 16 is 20% of 80.
Okay,
So subtract
400?
16 from 80, if that's how you want to think about it, and it would be 6,400. So notice that the change in the first year was 2,000, the change in the next year is only 1,600, etc. So the number of people is decreasing by 20% each time. So don't think after 5 years everything's gone, is the only reason I'm carrying that out.
Okay.
So after 1 year, we have eradicated 20% of the diseased people. Right? And we're trying to figure out how long will it take until we only have 1,000 diseased people left.
Okay.
How many years will it take so that there's only 1,000 diseased people left in the population? You with me?
Alright.
Now our equation now is y is equal to y naught times e to the kt. This would follow immediately from that if we solved it again. Right? Okay, now I know after 1 year, y is 8,000. And I'm going to use this to get my k. So I know that 8,000 is equal to 10,000 times e to the k times t. Question, is my value decreasing with time or increasing with time?
Your value is decreasing.
It's decreasing with time. So this k has to be a negative number. That k is going to be a negative number when my value is decreasing with time. It's going to be a positive number when my value is increasing with time. Okay. So now we're solving for k. So, first off, divide both sides by 10,000. What's 8,000 divided by 10,000? It's 0.8, right?
Yeah.
Yeah, 8/10 or 0.8. So this is going to be equal to e to the kt.
And then natural number.
Natural log both sides gives me that that is equal to k times t.
Yep.
Where our t, sorry, we knew our t was 1
T is 1.
after 1 year. And so finally, there we go. I know that my k is just equal to natural log of 0.8. Since 0.8, question, what is the natural log of e?
1.
1. So if your value inside here is less than e, it's going to be negative.
And that one is.
So our natural log of 0.8 there is going to be some negative number. It's approximately, does it give it?
223.
Negative 0.0223. So this is approximately minus 0.223. So there's our k. So now our equation right here, we now know the k. Right?
Okay, yeah.
And now we want to find the time that gives us a population, an infected population of 1,000.
So you, for y, you put it in 1,000.
So yeah, plug in 1,000 for y is equal to 10,000
your k
times e to the kt.
k is that.
Where k is that number?
Okay.
So divide both sides by 10,000 and we get 0.1
Yep.
is equal to e to the kt.
Natural log both
Take
sides.
the natural log of both sides.
And then plug in your k,
Plug in
your
K.
t.
So then we're going to get
Or you plug
that.
in your k and then move it.
Yeah, I think you're good to just jump all the way to here.
Yeah.
Right?
Mm-hmm.
And so natural log of 0.1 divided by k. You plug that into your calculator.
10.32.
And now, negative number divided by negative number is going to be a positive number.
Yeah. I mean, you can't negative that.
And it should come out to approximately, and you said 8.2?
10.32.
10.32.
10 years.
10.32. So it will take roughly 10 and 30 years for the population, for there to be only 1,000 infected people in the population.
Crazy.
All right. One more example, and then we'll be done. So example 5. Last example in the whole class. Oh, wait, there's an example 6.
Yeah.
Oh, did we just do example 5?
No.
Oh, we did 4.
No, we did 4. Okay, example 5. Yeah, we gotta do example 5 too. Because this one gets to carbon dating. You've heard of carbon dating before. What's carbon dating?
It's like looking at the decay of a carbon atom as something to determine how old it is. I think. Something around that. It's a way of dating an object.
Yeah, so do you know what an isotope of an atom is?
Yes, yeah, I think so. Yeah, it's a atom. It's another version of an atom with a different amount of neutrons.
With a different number of neutrons, but the same number of protons. So, carbon, what number is carbon on the periodic table?
1.
3.
Wow.
3.
What?
Oh, carbon? Oh,
Yes.
I thought I-
What number is carbon on the periodic table?
Is it 8?
Hydrogen is 1, helium is 2,
Is it 8? I can't remember. I'll Google it.
it's 6.
Oh, that makes sense. I'm done.
So, carbon, that means carbon has 6 protons in its nucleus. Now, if we're talking about carbon 14, that means that the total number of things in the nucleus is 14, and so that means it has 8 neutrons. If we drew out its whole nucleus, and so 8 neutrons. And that would be a carbon atom, and then it would have 6 electrons orbiting it. Roughly. There's my beautiful carbon atom. Okay, so this is just one isotope of a carbon atom. There can be a carbon atom that has less neutrons, and there can be carbon atoms that have more neutrons. There's no such thing as a carbon atom that has more protons or less protons, because how many protons it has dictates what atom it is.
Right.
If an atom only has 1 proton, by definition, it's hydrogen.
Right.
So, different isotopes of carbon. Now, it turns out that carbon 14 is a relatively unstable atom. What does that mean? It means it's pretty easy for it to break apart into 2 separate atoms and decay. That's what we mean by decay.
Like nuclear bombing.
Nuclear bombing does something similar. It uses fission to break a bunch of uranium atoms all in one go. But one little carbon atom breaking is nothing. Don't worry about it. I know there's all this notion of if you split an atom that somehow creates some giant explosion. No. That is not a thing. So if you break it, it just splits into 2 smaller atoms and they go their merry way. But carbon 14, it's relatively unstable, which means that these things break pretty fast. And I can't remember what its half-life is. It has to say in the problem somewhere, 5,730 years. 5,730 years. If you sit here and you stare at that thing for that short interval of 5,730 years, there's a 50% chance it will decay.
That's pretty cool. Sounds like a good.
So if I get 100 of these things, and I watch them for 5,730 years, then roughly half of them will decay, and I'll only have 50 left. That make sense?
Yeah.
Now, as you are a living person, composed of carbon, and you breathe in all that carbon from the atmosphere, your body uses that carbon to build up carbon chains inside of you. The proportionality of carbon 14 in your body is pretty much the exact same as it is in just the atmosphere around you.
Oh, cool.
When you die, that carbon 14 is you're no longer breathing it in, using it to help build up your body. And so the carbon 14 in you starts decaying. And so I can say, if 1/10 of our atmosphere is carbon 14, when you die, 1/10 of your carbon should be carbon 14.
Okay.
If I see instead only 1/20 of your carbon is carbon 14, that says you've been dead for a long time.
A long time.
If half your carbon 14 has decomposed, then that means that you've been dead for 5,730 years. And so this is how we can age things. This is how we can guess the age of things. You go get some bone and someone says, oh yeah, this guy died 2,130 years ago roughly. Where are they getting that number? How on earth are they coming up with that number? We're going to come up with that number.
Well, that's only 5,000. We can't do millions.
Yes, you can do millions, you can do billions, you can do whatever you want.
Wow.
It's also the way that we determine how old dinosaurs are. We'll do that.
Excellent.
We'll do that. So, here's the one that we're going to do. So, carbon 14 has a half-life of that many years. Find the age of a sample with 10% of the radioactive nuclei originally present have decayed. Okay, so, initially, so we got some bone here, and we measure it, and we decide that it only has 90% of the carbon-14 that it should have. You with me?
Yeah, but.
So our equation is going to be y equals y naught times e to the kt, right? Huh?
Where's 90 or 9? Never mind.
Okay, because we know that the half-life is 5,730 years, that tells me that in 5,730 years, you have half the carbon-14 that you initially had.
Okay.
So I know that 1/2 y naught, half of what we started with, is equal to what I get when I plug in 5,730 for time. If I plug in 5,730 for time, I end up with half the carbon-14 I started with.
Yeah.
Okay.
So now we can use this to solve for k,
Okay.
for our particular specimen, right? Okay, so divide both sides by y naught, and I'm left with 1/2 is equal to e to the k times 5,730, right? Natural log of both sides, and I get natural log of 1/2 is equal to k times 5,730. Divide both sides by 5,730, and I get k is equal to natural log of 1/2 divided by 5,730. There it is, which is approximately, does it give it to us? 1.2 times 10 to the negative 4. 1.2 times 10 to the minus 4. You okay with scientific notation?
Yeah.
1.2 times 10 to the negative 4. Just remind you that's the same thing as shifting the decimal place 4 times towards making the number smaller. So that's the same thing as 0.00012. Right?
Yeah, I want to.
Okay, so there's our k. We got our k. Now we know in our sample that it has 90% of the carbon-14 that it had when it started. So right now it has 0.9 times whatever it started with. I want to calculate what the time must be to make so it has 0.9 of what it started with.
Okay.
You with me? Okay. So now we just solved this for t. Oops, sorry.
Yeah, you
I missed my y now.
There we go. Well, don't
Okay.
know what y naught is.
We have no clue what it was.
Yeah.
Notice that in all this time, I never need to know how many carbon-14 atoms are in your body. I just need to know the proportionality of them to the rest.
That's pretty cool.
Okay.
All right, we can't count atoms. Too hard.
So how do we find the proportionality?
How do you find the subsample? So you do have to count them in some small sample. But I don't need to know what they are in your entire body. So I just take some piece of the bone and I get the ratio, and then from there we're good.
That makes sense.
Okay, but anyway, so we got this. Divide both sides by y naught, and I get 0.9 is equal to e to the kt. And that's why the y naught doesn't matter. We keep dividing by y naught on both sides, canceling it out.
Oh, yeah.
They're seeing it in the math.
Of course.
Okay, and now natural log of 0.9 is equal to k times t. And so t is equal to k divided by natural log of 0.9.
We have.
Is that
The
reciprocal?
author, they use the equation, they put a minus right here. Rk is actually a negative number.
Yo,
It's negative of his, so
Isn't it-
Rk is a negative.
log of 0.9 over k?
Yes, thank you. So this should have been natural log of 0.9 over k.
Yeah.
And now natural log of 0.9 is going to be a negative number. Rk was a negative number. Negative over negative is positive. And it comes out to roughly, if you calculate it,
871.
871. So, if our sample only has 90% of the carbon-14 that it should have, then they died roughly 871 years ago.
Okay.
Right? We could have now repeated this whole process and said, now let's pretend it's a dinosaur bone. And let's say that it only has 0.1%, or it only has 10% of the carbon-14 that it was supposed to have. I don't know if that will take us back far enough. But if this would have been 0.1, if you do this division, I don't know if one of you has a calculator, do natural log of 0.1 divided by 0.00012.
Isn't. Oh, because there will never be no carbon in it.
Natural log of 0.1.
Natural log of 0.1 divided by 0.00012.
0.00012.
You missed a 0. 0.00012.
3 O's?
Mhm.
Okay, I got that.
Oh, okay.
So that's negative.
But this should be negative, so it doesn't matter. Ignore the negative, but should be some big number in terms of years.
365.
19,188.2.
19,000 what?
188.
188. Okay, so that wouldn't really give us a dinosaur, not by a mile, but that would give us something that is definitely more than 5,730 years ago.
Yeah.
First human.
Whatever. But you see how you could generalize this for any amount. I guess we could have done the reverse. We could have checked, just plug in after 2 million years and see how many it would have and get an approximation that way.
So, how old are dinosaur bones?
I don't know. They're millions. They're on the scale of millions,
Like
not
hundreds
thousands.
of millions of years.
365 is what I thought. Or 360.
Well, there's a range of dinosaurs.
Yeah, it's going to be a big range. I think like the more famous ones are closer to the 60 million years ago mark, but I could be wrong.
I think it's about right.
Oh, well, anyway.
It doesn't matter. But the point is, you see how the process works.
Yeah.
Yeah.
Okay, let's do our last one now. Promise last one.
Trust.
Because I also have to introduce Newton's law of cooling. We can't not cover that.
Obviously.
So, this is not what the last thing.
This is the last thing now. Newton's law of cooling. It's still just the exact same type of thinking. It's just a different story problem.
Oh, same plug and chug though?
Same plug and chug.
Okay.
So Newton's law of cooling depends upon the fact that what determines how fast my coffee cools down is how much hotter it is in our surroundings.
Or how much cooler?
How much hotter or how much cooler? If we're heating something up.
Doesn't that... Okay, yeah.
Depends on which way we're going. But we'll think about it as something cooling down. So something really hot cooling down. And so the rate of change in, we're going to use H for temperature because, well, the H comes from heat, but also because that's what the book does. So we're going to assume that the change in heat with respect to time, whatever that is proportional, so some constant,
Yeah.
times however much hotter your coffee mug is than the environment. So H minus H sub S being for the temperature of your surrounding.
Okay.
You with me so far? So if we make this assumption, which is what Newton's law of cooling does, you might have already done this in some of your physics. I don't know if you did some of it. Bodies radiating out heat.
Maybe.
Probably not, because you can't use differential equations. Body radiation?
What?
Never mind. Okay. If you would have touched it, I mean, it's when you do thermodynamics, typically. Doesn't matter. Okay. We'll say no, you haven't. Okay, so here it is. If I let y now be my function which tells me the difference between how hot my coffee is and whatever the surrounding is. So I'm going to use y, it's going to give me the temperature difference between my coffee and the surroundings. And so y is a value that's going to decrease with time because my coffee is going to cool down if I bring it in this room. Okay? So let's let y be that. Then what is dy dt equal to?
We have no t.
Huh?
We have no t.
How does y change with respect to t? Well, that's going to be just the derivative of this side with respect to t.
Yeah.
So it's the derivative of the temperature of my coffee, the change in the temperature of my coffee with respect to t, minus H sub s here is a constant. It's the temperature of the room. The temperature of the room does not change when I bring my hot coffee in here.
Negligibly.
Not in any way that we care about.
Yeah.
So that's a constant, and the derivative of constant is a 0. So if I let y equal this, then dy dt is just dh dt. And so rewriting this equation, dh dt is the same thing as dy dt. This equation now becomes dy dt is equal to k times y. And so this has the exact same form as all our other equations,
Yeah.
just where y is equal to that. And so if we were to solve this, we would get this exact equation. Substituting back in, we get y is equal to y naught times e to the kt, where h naught is whatever the initial coffee of my temperature is. then y naught, the initial difference, is right there.
Yeah.
Because y gives me the difference in temperature between my coffee and its surroundings. Good? Just plugging that blindly in. Plug and chug, just like you like. Okay, now let's get the actual problem. So the actual problem is a hard-boiled egg. So I boil my egg, and I boil it to a temperature of 98 degrees Celsius. So the initial temperature of my egg is 98 degrees Celsius. Okay? And I put it in some water, so the temperature of the surroundings, the water has a temperature of 20 degrees Celsius or 18? 18. Good so far?
Okay.
Yeah.
Okay. So let's see. A hard-boiled egg at 98 degrees Celsius is put into a sink of water at 18 degrees Celsius. After 5 minutes, the egg's temperature is 38 degrees. Assuming the water has not warmed appreciably, how much longer will it take my egg to get to 20 degrees Celsius? So I come back after 5 minutes, and I measure the temperature of my egg. And it's still at 20 degrees Celsius. Oh no, it's still at 38 degrees Celsius.
Yeah.
And I know I can't eat my egg, it's going to burn my mouth, unless I get it down to 20 degrees Celsius. So I'm wondering, how long do I got to wait to eat my egg? Right? Trying to figure out how long I can wait to eat my egg.
Your little calculus.
Yeah, so you whip out your calculus and you solve it really quick. So you know that h minus, what's h sub s, 18.
18.
The temperature of my egg minus 18 is equal to my initial temperature minus the surroundings. My initial temperature of my egg was 98, minus 18 is 80. All times e to the kt. So here's our equation. You with me?
Yeah.
I know that when t was 5, after 5 minutes, the temperature of my egg was
What was it, 20?
38 degrees,
38.
right?
Yeah.
After 5 minutes, the egg was 38. So I know that we got a 38 here after 5 minutes. And now I can use that to solve for k.
Okay.
What's 38 minus 18?
20.
20. 20 divided by 80 is?
40. No.
20 divided by 80 is?
4.
1/4. 20 divided by 80, not 80 divided by 20. 1/4 is equal to e to the k times 5.
Yeah.
Take the natural log of both sides. And we just get k times 5.
And then move the 5.
And then move the 5. So k is equal to the natural log of 1/4
20.
divided by 5, which is approximately 0.28, negative 0.28. Okay, so that's what that comes out to approximately.
And then we need to figure it out for when it's going to be 20 is what it said.
And now we need to figure out, when is the temperature of my egg going to be 20 degrees? Or in other words, when is the temperature difference going to be?
So 28.
Well, we'll just plug it in. Okay, so now I want to know the time for 20. So 20 minus 18
Yeah.
equal to 80 times e to the kt. But now we know what k is. K is negative 0.28. So now we solve this. What's 20 minus 18?
It's going to be 1/40.
Okay.
equals,
So, jump ahead. Natural log 1/40 is going to be equal to kt.
and your
Or in other words, t is going to be
0.2. And then it's going to equal
natural log of 1/40
over negative 0.2.
over k. And now negative over negative better come out positive. And when you do it,
13 or something. About 13.
then you should get about 13 minutes. And so you've already waited 5 minutes, and so you're going to have to wait 8 more minutes to eat that egg if you don't want to burn your mouth.
8 or 13.
8, because you already waited 5 minutes,
Oh, that's total. That's
right? So the total waiting time is 13, but 8 more minutes. Now, just to give you one more application of this, this is actually used all the time in forensics to determine when somebody died.
Yeah.
Really?
Yeah, so once you die, we know your initial body temperature is roughly 98 degrees Fahrenheit. We know the temperature of the surrounding of the room that you're in. If you die in a place where the temperature is relatively stable, then we can calculate this pretty good and figure out when you died, based off of how fast your body cooled down.
You can't just take, you're saying they take the temperature where they find the body?
Yes, so I come across a dead body, I measure its temperature, and I measure the temperature of the room around it. And based off of what temperature it's currently at, I can calculate when that person died.
Using this?
Yes, using Newton's law of cooling.
That's so cool.
This is the exact math that backs that up.
That is sick, actually.
And so that's why then it becomes very important. A policeman can, a detective, they can say, okay, this person died 24 hours ago. And so now, knowing exactly when they died, or roughly a good window, helps me start narrowing down on suspects pretty easily. If you were in town 2 days ago, but you weren't in town yesterday, then you couldn't have been the killer. Because they for sure died in that 24-hour window, or whatever.
Mm-hmm.
So yeah, Newton's law of cooling. Newton's law of cooling was also one of the first ways someone tried to estimate the age of the Earth.
Really?
Yeah, they calculated how much heat the Earth was radiating out. They thought the Earth must just be cooling down. And so, they did some calculations to try and approximate how old the Earth was.
Did that work?
No, it's way, way off. Because the Earth is not just cooling down.
Yeah, right.
This is before something called the weak nuclear force was understood. And so the Earth is actually constantly heating up due to radioactive decay.
Right.
And while that's small on our scale relative to the whole Earth, that is a very important part of the process. And so the Earth is actually still producing heat all the time. It's not just some big ball cooling down. That's not a valid way to view the Earth. Huh?
So, did the other planets do the same thing?
If they're big enough, yeah.
Yeah, it depends on a few factors. So, for example, Mars is what we think of as now a dead planet.
Yeah, so Mars is completely cooled down, so the core is solid.
And so, to what extent that's having any effect now is not as comparable as it is for the Earth.
So the Earth is pretty new as a planet?
No, they're both the same age. It's just it had more going on.
Earth is 3 times bigger than Mars.
Bigger, really?
Yeah.
Oh, I did not know.
But it's not just the size of the planet that matters as much. It also has to do with like the atmosphere and stuff. For example, Venus has a lot going on.
Yeah, Venus is really...
I'm not sure if Venus's core is hotter than Earth, though.
Uh,
I would be surprised.
yeah, that would be hard to figure out for sure.
But Venus does have the hottest surface temperature of any planet.
Even over
Yeah.
Mercury.
But it captures a lot of the heat that it radiates out because of it has such a thick atmosphere.
Mm.
And so the atmosphere can act as basically a coat for the planet, helping retain stuff.
Yeah, it's pretty cool.
Anyways, so there we go, Newton's law of cooling. Last thing we're going to talk about, differential equations. Look at you guys. The crazy stuff you can do now that would have looked like a bunch of gibberish at the start of the year.
Oh, that's pretty cool, actually.
And there you go. You're done with Calc 1. Ready for physics next year.
Yippee.
We don't need
Physics
more.
is like that, then heck yeah.
That is, yeah, got a little taste of physics right there.
Is that actually how it is?
I don't understand the question. I was
That's-
not lying to you, or at least not intentionally. All right, any other questions?
Are we doing anything more in calculus this year?
Yes.
I might come up with some filler stuff.
Are we just going
I'm
to
gonna
We'll see.
Push the test back.
That would
I
actually be really
have
nice.
a lot coming up this week.